Okay, it's time to get started. Today we are going to cover 4C, and we're going to skip 4B. Last time I was told we did 4A, so if you guys are remembering, this is good. 4B is 16 slides on shells. I'm not going to do shell stuff. It's not going to be, but you can look at 4B if you're interested in finding out about shell information. 4C is managing processes. It gets into some terminology about daemon processes, runaway processes, how to check processes on a Linux system. Which is useful. And then I'm going to cover 5 today, which is going to be Unix admin tools. So let's get myself organized here. Oh, here we go. I got 4C. I'll start it back up. This is a small little lecture that kind of goes through the concept of the process in the Unix system. And for those of you who just walked in who missed my little announcement, I'm going to put it on YouTube. that about an hour and a half ago or so, I guess the faculty and the administration got the official message that we got our WASC candidacy. So we are definitely on the road to accreditation. So we just got our WASC candidacy. There's probably going to be an announcement, hopefully, that's going to come out to the students, like probably by the end of today, maybe tomorrow, maybe, I don't know. You would think that they'd be, well, they probably are, but they're too much excitement probably right now, so they have it. Once the excitement goes away, then I'll tell the students, I guess. But yeah, no, I should be happy about that. So, okay, back to the boring stuff. Managing processes. Well, you want the candidacy. Not to keep talking about the candidacy because it will raise the value of your degree, essentially. And the candidacy is just as if we were accredited. So everything that you're doing now counts towards your accredited degree. So, which is nice. Nice. Good step forward. You know what that means? Tuition increase. No, I'm just kidding. Kidding. I don't know. If I were to look into a crystal ball, I think I'd predict it, though. So, pros and cons. Okay. All right, back to Unix. All right, managing processes. Let me get focused here. We're going to talk about Unix processes, running programs, monitoring progress processes, and killing processes. All part of the Unix process concept. And I know this is probably redundant for some of you who have already been programming in threads and processes, but it's core to Unix. So it in a Unix class, it kind of goes without saying. It probably should be discussed. So what is a program? Well, a program and a process are pretty much the same thing. Every time you run a program in Unix, you're starting a new process. And so a program is a file that can be run, and by terminology, it's the saved executable binary code that's residing somewhere on the system. And or it's a shell script. It's a text file that can be executed. So in terms of the process is what is called a running program. So before the program actually starts running, it's a program. When it actually gets executed, it's running, it's in memory, then it turns into a process. I mean, basically that's what the definitions are telling you. But a program is a process when it's running, and it's not a process when it's not running. So when it's loaded into physical memory, it's stored in virtual memory, it's swapped in and out, it's used, which brings up the virtual memory concept. Every operating system, including Unix, has a virtual memory management system. And in the Unix, it extends out the amount, and really in Windows and the Mac as well, it extends out the amount of physical memory. Plus, also we know writing to physical hard drive, physical memory, even secondary media like hard drives and things, is very time-consuming, very expensive in terms of calculations for reads and writes, and for speed. So if we can cache and kind of create a virtual memory abstraction of the physical memory, we have faster access to it, essentially, by an abstraction base. So in the beginning, it was basically used for faster kind of access method. However, we can extend out the amount of physical memory. So we can have more virtual memory than we have physical memory. We can essentially create a huge memory area for our running programs. And every one of our processes gets stored in memory, and then we go back and we look at the process, we can kill the process, and we can access the process if we're looking at it from a virtual memory management perspective. So Unix has a size of a swap, which is the amount of usable memory. And then we have the physical memory, or the RAM, that's mirrored to the swap. Sometimes we have these things called swap drive. Sometimes we have, in fact, it's the physical drive. It's a hard drive that gets formatted, and they call it a swap drive. It's really nothing more than taking physical memory from a secondary memory storage media, and making it into virtual memory. So it's like making more RAM out of, less RAM that's there. And you have to imagine in the old days, we were working on limited hardware systems, a very small memory, physical memory allocation, and in fact even today in embedded systems devices we might not have a large amount of memory. So we can take and create a swap drive, and the more RAM that we can create from a virtual perspective, the faster everything's going to run, because we have more room to load processes and switch them around. And so swapping is kind of a common thing that goes on. So it moves, the concept of swapping is, by definition, it moves pages to and from memory, and it swaps out something when needed. So it's usually a just-in-time type of swapping mechanism that goes on, because why waste CPU resources to swap when you don't really need to? It's only when you run out of memory. And the page is a block or a unit of RAM that's allocated either as a swap page or as a memory unit. Here's a BSD Unix. This is actually, it's what you get on a MacBook actually. In the OS X environment is BSD as a variety. And the RAM here, and then the swap, it basically extends it. Gives us like twice as much capability if we create a swap. I don't even know if that Mac OS actually uses a swap drive, but I believe it does. It partitions a bit of the hard drive space into a swap disk. And when you notice this when you start doing Linux installs, and it says, asks you, do you want to create a swap drive, and how big? And there's a calculation for it. If you create too big of a swap drive, it's too much memory. The searching through the memory is too time consuming. So if you don't have enough, or if you have too much, it causes problems. So you want, there's a balancing act to get just amount. What works better than RAM or swap? Well, it's controversy, actually. It's a huge controversial topic even in today's modern day operating systems in terms of the allocation. And I believe I talked about the process lifecycle before in this class. If not, here it is again. When you create a process, because this lecture is all about processes, it comes into a new state and then it gets admitted into the process system. The kernel keeps track of all of the running programs, the processes in the system. There's a process control block, which is nothing more than a data structure that's held by the kernel, for which every new process gets an entry in this table, and then it gets a process ID, and it gets information stored about its particular state. And this really works hand in hand with virtual memory, because we have CPU scheduling and memory management, and we have processes. And the memory is going to basically occupy or be used as a general resource for both the CPU scheduler and the processes. So pulling a process out of the PCB, running it, putting it into a queue for I/O access, for CPU access, allocating resources, memory to it, keeping track of the memory, rotating it through all of the instructions to actually perform the work that the process is supposed to do. It's probably one of the most complicated parts of an operating system in terms of, and Linux is fairly straightforward, which is not too bad. But so the process itself, the new one gets admitted, goes into a ready queue, and then it gets a chance. It gets dispatched by a CPU scheduler to run, and then it goes back into the ready queue. So it goes back and forth. It might have an I/O request, and then it might wait for some I/O to complete, and then it goes back into the ready. Eventually, hopefully, it's going to be done, and it exits out of the system. But at any one moment in time, processes go in and out of different states. So process states are kind of the interesting part. And then we have different process components that are associated with the processes. And it depends on the process system as to how memory is allocated. In some systems like Linux, Unix, which we're studying for this course, the parent process basically creates a child process, and the child process gets a copy of the parent's process memory space. And then if that child makes another, threads another process, then it gets a copy of that child's memory space. And everybody's connected through a hierarchy. And really, just from the start of the Unix kernel, the hierarchy is created. And it's created with process number 0, and then everything is ordered sequentially upward. And everybody belongs to somebody else. So the programs can talk to themselves, communicate back and forth with thread support or process support using signals, mutexes, and stuff that's supported by the kernel. And it's a really elaborate process system. Operating systems like Windows don't have that. You can't even create a process from a user level in Windows. And Unix, Linux, you can create a, use a pthread library, POSIX thread system call interface essentially, and create threads. You can't do that on Windows. So in terms of the process components, the address map, this address space map, which is the configuration for what address in memory and what section and how much memory each process is allocated in Unix. It's fair. Every process from the user mode gets the same amount of memory, and every child that's created from each process just gets a stamp, copy of the parent's memory by default. And usually there's no swapping in between different processes. Each process is self-contained, and you can create shared memory if you want to. We have different statuses of processes, which is kind of interesting, and this is what I kind of would like to cover as well today, is the concept of the zombie, the concept of a sleeping process, a stopped one, a running one, and a runnable one. Each process has an owner in the system as well, and each process has can block signals, can send signals, and generate different events and activities going on that we can use for interprocess communication. Each process has a priority, and we also can keep track of the resources that each process is being that's being used. And we have process ownership in terms of users, real users, groups, effective users. Much more than you would think from a Windows perspective. A lot more simplified in Windows, I would say. In a Unix perspective, the user who's starting the process is the real user. And we have a user ID and we have a group ID. And this kind of plays into the permissions concept. And one of the assignments actually has you set permissions for groups and users and things to get you familiar with running the change mod command. Effective user permissions are the effective users, the permission for the process. It might not necessarily be the user, the real user, but it's effective because it's granted. So the effective user ID number, effective user group ID number, if you have them separated out into group, that would be good as well. So these would be the permissions that were set. The process life cycle. What we have is a parent process that forks a child, as I mentioned before, and the memory is shared between the family and the hierarchy. We have process identifiers, which is the PID, or the process ID number. And it's kind of a variable you can set and use yourself when you're doing thread and process programming. PPID would be the parent process ID number. We can't really we know the parent. Every process knows its parent, but it may not know itself. So it can always get back at its parent. It needs to know its parents because when it dies, it needs to relinquish itself, clean up the memory, and go back. Kind of goes up one level, and it signals automatically to the parent that the child has gone away, which is how we can keep track of how many processes are out in the system. When the child finishes here, it sends a status message back to the parent. So we have two kind of different types. The zombied process waits for a parent acknowledgement, but doesn't get it. So it means the parents died. So the child can never actually complete, which means some of the resources for the child are left, and it's zombie. Imagine those horror movies, the guy's walking, it's half dead, half alive, and it's just zombied. It's out there, it doesn't belong to anybody. I mean, it can't signal back to the parent. They come up from the dead, don't they? From the ground. The dead people in the ground, they come up and they come back to life. But they're supposed to be dead, but they can't signal back to the parent that they're dead. So they're stuck in the in between. So that's where the word actually comes from. And the demon sits around and doesn't belong to anybody. It's out there. It's out there, but it's not dead. It's not supposed to be dead. Zombies are supposed to be dead processes who signal back to the parents that they died, but the parent never got the signal. Daemon processes are out there to do work. You create it, and then the parent can die on purpose, but it's running. It's a running process, and it's out there doing something. It's not taking up wasted resources. It's performing print jobs. It's looking for doing accounting. It's doing user management stuff. There's a ton of daemon processes that are created by the kernel for kernel work. Orphans. That's when the parent the process ID, the PID1 or the init, that becomes a parent. Because its parent has gone, but it becomes the parent and it can fork off new processes. So in terms of running a command, and you see these words used a lot, and sometimes it depends on the scenario whether or not an orphan process was created. whether what a zombie process was, and it's basically indicating the state of the process. It's a orphan is a child acting like a parent because the parent's gone. So, but they're still running, they're still forking off processes, but they're orphaned. They don't belong to anybody. So they have their own process group. Init is actually an orphan that's created, because init's the first process, PID1, that is the parent process of the kernel that gets created by the kernel, but it doesn't belong to the kernel anymore. The kernel creates this, when the kernel is done booting up, it creates this process, and then the process is out there on its own, which is why it gets labeled as an orphan, essentially. Because technically, I guess it does belong to the kernel as a parent, but the kernel has no control over it. The kernel can't kill it. So user can't really kill it either. So it's kind of a protected process, but it's the parent of all of the user level processes in it. So when you run a command, you type in the command name, obviously. And in the shell, you get searches for the command. This is pretty much the order of execution when you run a process. If it's found, then the shell forks the command, which means the shell creates a process for you. And it opens up and essentially the process starts. So your program execution. And how's the command found? It's usually found by the path, the environment variables, and which will display the full path to the command. So you type in which and it'll give you that information. Be aware of the dot in your path as well. The dot / to be the current directory as an example. And then we have background and foreground jobs that run in the Unix environment. And this is not a negative thing. A lot of people for some reason think that background jobs are negative or something. They're really actually, it's just a multi-processing environment, the background jobs. Foreground jobs are pretty easy to comprehend. Something's running in front of you and you're getting the output. And returns control to the shell after it finishes and after it's done. Most common usage, everybody runs foreground processes. In the background, you can run the same program that you run in the foreground, you can run in the background. You put the ampersand after the command, it automatically loads it in the background, but it returns immediately. It doesn't wait for the process to finish. So it allows you to run very, very long jobs. If you run a short one, it comes back immediately. Like if you ran ls in the background, you're not going to notice it. Whether it runs in the foreground or the background, it's all going to look the same. If you run a huge backup, it'll give you the ability to run another command. It's running, but it gives you the command prompt back and says, okay, now you can run something else. So you can run things concurrently and create a multi-programming, multi-process. Here's the daemon I talked about. I forgot the daemon was actually in here. Daemon is actually a much older form of daemon. Daemon, D-A-E-M-O-N, as opposed to daemon. Has no particular bias towards good or evil. A demon, you know, like an evil thing, but rather serves to help define a person's character or personality. So special programs which perform some task without any intervention is a daemon by definition. So starts in the background, often at the system startup. Kernel does a lot of daemon processes, creates a lot of stuff, and it's because it doesn't work with the user. It doesn't need any user interaction. So it just runs in the background, runs all. You can do your own daemon processes, actually. In fact, a scheduling program would be just like that, you know, like 5 minutes before lunch, a little window comes up and says, hey, go to lunch. Ah, thank you, daemon. You close the window, and 5 o'clock, you say, hey, go home. Oh, okay, good. It's in case you forget those important things in your day. So, the name of most ends with a D. The name of most ends in D. Name of most. How weird. Name of most commands, maybe, ends in D? I don't know what that means, really. It's been a while since I've looked at this slide set, actually. Name of most ends in D. Most of the daemon processes are out there. Ah, actually, that's probably correct because there's a scheduler that ends with D. The character D in the name, so. Anyway, yeah, the scheduled ends with D. And there's a couple of other common kernel daemons that are created. But the printer ends with an R, so I don't know. Anyway, FG, BG, and jobs. These are some Unix commands that you can type in to work with your processes. FG obviously is going to give you foreground, BG is going to give you background, and job is going to give you all of them. You can also type in PS for processes, and that will give you the same information as jobs. Jobs just gives you a little bit more user-friendly output, essentially. So you can switch between modes, foreground and background. So you can send signals you can send a signal to stop a process, or to bring it from the background to the foreground, and that's what the FGs and the BGs are doing. So run a process in the foreground, run it in the background, or jobs lists all of the child processes that are created for that particular shell that you happen to be in. So it gives you some flexibility. And we all know about signals. I think I covered that in the first couple weeks of the class, but it seems like it was a while ago by now. Basically, it's here's a signal used to communicate with processes. The common ones are like the Control Z or the Control C. On your keyboard, when you're pressing Control C, you're actually signaling. People remember this from the old DOS days when something got, look, the command window, it's stuck. This is back before you could just let it go and just open up another window. When you're stuck at a command prompt, your computer's frozen until that command finishes if it's running in the foreground. So you press Control C a couple of times and kills it and stops it. So terminates the process. Or you could do Control Z to suspend the process. It doesn't really terminate. It just leaves it running in the background and it gives you a foreground prompt. Kill, which is actually a word. You can type in a command. Kill with the a signal for a process ID. So you can kill it now, which means don't wait to close it down gracefully. And then you also have to enter a process ID because you don't want to kill everything in the system. It would be like rebooting your computer, essentially, resetting it. It doesn't do a reset, however, not to be confused with that. So it sends a signal to the process ID to shut it down. Very similar to a Control C. The default is to terminate the process by default. You don't have to terminate it, though. You can kill it with gracefully. Let it save, let it shut down when it needs to do. Some common signals: hang up, interrupt, kill, quit, a software termination, a stop, in terms of what's going on functionality-wise. So some of the common signals you can access by name, by this abbreviated name here, or by the signal number. And what you're doing is essentially either watching for a signal, catching a signal, or sending a signal, and communicating with the kernel, with the process states, with the running processes, and communicating via the signal interface. You don't really see signals until you start writing shells, until you start writing threaded applications, and then all of a sudden signal, it's a form of communication between the processes. So, process priorities are also important to consider. As I've been mentioning so far, all kernel level processes are generally at a higher priority. And it's because they need to be run. If they're not run, the system's not going to run correctly. And so the lower level processes, well, those are the kernel. Those are the user mode processes. Everything that's low priority is user mode. Because your jobs don't need to run as important as kernel. So, and then between the low set, you can set your own user level processes, the priority essentially. And what you can do is essentially tells you how much CPU generated time is actually given relative to other processes. So remember, before we have the CPU scheduler, it's allocating CPU time for each one of the processes that the kernel is pretty much managing. And you can tell the kernel from the user mode, and you can't set priorities. You can't change anything from the kernel perspective, but for your user processes, you can say, hey, this one's more important, or that one's not as important as this one is. And you use these commands down here, the settings for nice, for renice. So it sets the priority value at start to nice, or to renice, to change the priority range, to give it less priority. It's nice. Be nice. Share the CPU. Be nice, which is where that comes from actually, which means you're not going to necessarily get the highest priority. You're going to get a lower one. We're going to put everybody else in front of you first. You have to let everybody else use the CPU. Because you might have a labor-intensive system, process that's running that's going to eat up a lot of resources, and when you run it, the whole system is going to run slowly. So you just tell it, don't run so much. So let everything else run a little bit more. So that's a nice system. System load. Average number of runnable processes. You can actually get the system load. You can benchmark the system load. You can see peak times in the load balance, hopefully. Measure how busy the system is by looking at the system load. Perform deteriorates as load of 6+ occurs. Let's say, good for creating a baseline. You get this by saying uptime. And so you can load the averages. And so it'll tell you, how many minutes the system's been up, average load time, stuff like that. In terms of monitoring processes, I mentioned before, when we saw the slide, it said jobs on there. It shows us the nice form of the processes in terms of their IDs and where they're running and how long they've been running and stuff. Well, PS gets you a lower level of detail. It'll sort by process ID and also sorts by CPU usage. So using the PS command is very similar to the jobs command. It just gives you more information and not quite as formatted. So it's more raw data that's being given to you, which is a lot more useful in some cases. And you can kind of see how there's differences in the implementation. The BSD is going to sort it by the percentage of CPU usage, and the other systems are going to sort it by process ID. So Solaris SVR systems. Top is a command that has full terminal screen display, where it's sortable. You can kill or renice a process, renegotiate its status, its priority. And top just gives you, again, another level of control over the same information. So top, PS, jobs are going to essentially be the functionality that you can use as a system admin to kind of play around with your processes, manage them. It depends. I mean, if you're looking at the ability to reschedule or to sort something, rather than looking at raw data that comes out, use top. It's full screen access versus a list that just is kind of running in it. PS and jobs is kind of like running an LS command on the processes. It just lists everything out and gives you that information. Top's a little bit more interactive. So information from the process, from the PS command that you can actually strip out. And you can use parameter settings, switches to format the output that you're getting from this as well. At a minimum, you're probably going to want the process ID, the user that owns the process perhaps. Maybe it's a priority or it's nice level, because you can set different levels of the user mode processes. Resident total memory being used, maybe the process state, maybe the amount of CPU time or memory it's being occupied, maybe the CPU time used, maybe what command are we running, what program did this user run in this process, which might be helpful. In terms of if it's a backup, we could probably just pause it maybe. Or maybe the backup shouldn't be running in the middle of the day. It should be running at night or something. So helps you a little bit. There's a directory in the file system called proc, P-R-O-C. And that's actually the name of the directory in the file system. And it's actually part of the file system. It's a pseudo file system that keeps track. So it's the interface to the memory-related kernel data structures. So it's... I wouldn't call it a cache. I wouldn't call it a permanent storage either. It goes away when you shut the computer off. But it's giving you information, and you can query proc to see what's in the memory, essentially. You can't query the memory. You can't just do, like a file system, you can't just search through the memory and see what's there. It's not accessible. Instead, what the kernel does is it gives you this proc file system. You query the file system. You print out, you search through proc to see what's running in memory. What's that memory being taken out? What's in there? What's the temporary value? What's whatever it happens to be looking for. So it's your interface to the memory-related kernel data. So each process ID has its own directory in proc, and it's all ordered by the process ID. So you go in there and say, okay, what's going on? Here's some commands essentially that you can run on it. Symbolic links to the current working directory, to the program itself, command line options to show you the command line environment line options, the stats, process status, things of that nature. So you run essentially the commands to get the information from the directory, from the file structure. Yes?
Will it just list the processes being used by a single user or who are not logged into the system?
Depending upon your system administration privileges, it's usually this directory in the file system is only available to admins, and it's going to list everything. And it's going to be listed out by process. So each process, and it's just the memory that's being used and the contents of the memory. So it's good for troubleshooting problems, for researching, or looking for something in memory, finding something. It has limited purposes. But you won't use it like you'd use everything in the file system. It's just an entry in the file system to represent the memory that the processes are taking up. Represent the data that's being stored by the process structure. Runaway processes can eat up your resources. Yeah, a process that's running that's taking CPU time that should be dead, but it's not dead, or maybe it's just running and we don't know why it's running. Somebody started it by accident. Backups, you know, a lot of different processes. So you can, in terms of figuring this out, you can list the users and the process IDs and access a resource. As an example, fuser or ls OF to kind of get a list of these processes that are running and kind of, you know, figure out, well, you know, kill the process, clean it up, figure out what user ran what, and oh, the user's not even here anymore. As a classic example is that telnet users. You know, you log into a telnet system, you start something, and then you leave. Or you've closed the window, but you didn't log out. You started all these processes, and all this stuff's running, but your session's over with. So you're gone. Usually, from a telnet point of view, especially SSH, isn't going to allow anything to run after your session closes. So it's going to go ahead and automatically close that stuff for you. But in other environments, it might not. It depends on what program you're using to connect, what terminal window you're running, stuff like that. So, what do we got? We got lecture number 5 on yet more Unix admin tools. And then that was quick. That was 4C. It was kind of a quick run through on the process concept for what you need to know for basic Unix concepts. It would not be right to have a Unix course and not actually even talk about the process concept. And there's more processes in here too, more process information. This is going to look at the review of the file manipulation utilities that you're going to need for some of the assignments that you're going to do. Unix process system, again, from a different perspective, a little less on the commands, more upon the concept of the process and the threads. And then an overview of the shell concept as well, covered in here. And which is what, think about it, admin tools. This is really much what you're looking at in terms of system administration. So let's talk about file attributes for a minute. And I'm not going to go through all of it because I've already told you from a different perspective. I've already told you the concept of the change mod command. We'll see that again in the next couple slides to refresh your memory. But file attributes are kind of something that's stored in the file inodes, if you remember that. Not with the file. So it's not actually stored with the file on the hard drive, it's stored in the inodes. So we can manipulate the inodes a lot faster. So we can set directories, permissions, file permissions, and it can cascade the permissions from directory to file level. We have the file ownership by user and by group. We have the file permissions, read, write, execute, as we've seen before, and we can have file modification times. So we can, as a system administrator, you can kind of see who changed what, when. And we have different types of files, and the file system has regular files. That's everything you store in terms of a text file, a Word file, things of that nature. Directories. You all know what directories are usually. Links to things outside of the directory structure. Symbolic links, which are not a copy, not a rename, but a different way of accessing through the file system the same location, the same information. It's kind of like using a pointer, actually, where you've set a symbolic link to a directory and you're accessing the directory content through that symbolic link instead of going to the directory. Why do you want to do that? Actually comes in handy. You know, when you have directory names that are 25, 30 characters long, build number 542739 dash something or other, something or other, dash something or other. Why don't I just create a symbolic link, call it build. It's easier to type in, you know, so it's just kind of, and it's easier to find abstractly. So you can archive a bunch of build information, a bunch of different directory names, and keep it all organized, then create symbolic links. And you're accessing the same information in the same directory, but you're getting at it a different way. And then we have special files. Special files would be like the inodes and things of that nature that are created or searchable. Or special administration files, temp files, backup files, lost cluster files that might be created. Utilities for manipulating the attributes that we've seen before, the change mod. We've seen a lot about that. We haven't, I think we have seen the change group or change owner perhaps, but this is, I don't think I actually went through anything other than the change mod so far in this class. The change mod, we know we can change file permissions. We can change the file owner. So Mary was at the company. She created a bunch of files, and then Mary's gone. She moved to a different company. Well, all the files are owned by Mary. We could make all the files owned by somebody else. And take the entire directory that she was working with and make her replacement on those files now. So as a system administrator, when you go and just take a look to see, well, who owns that file? Mary. Who's Mary? Mary's not here anymore. Oh, it's Bob. Bob owns those files now. So it kind of helps in terms of resolving, you know, ambiguities and things in terms of ownership and groups. Also changing groups, because one of the things a lot of people do is an HR group, the testing group, this group, that group. If you make files belong to a group, then it doesn't really matter who owns them. They're all part and accessible. So whoever owns the file actually has access to it, or if it's in a group, they have access to it. Or if you change the permissions on it, they could have access to it. So if somebody else owns it but they made it public, then somebody else can have access to it. Which is the major security features of Unix, actually. That differs a little bit from the Windows environment. Similar, but not quite as tightly implemented, I think, on Windows. Only the owner or the super user can change file attributes. So what's a super user? Well, it's not an admin. Here's the other thing, too. So you set up this nice system, and you make everybody give everybody admin privileges. You've just defeated the purpose of setting up a nice system. So you have one admin, normally, only one admin. You can grant admin privileges to other users. Or you can make them super users, which means they have almost everything the admin does, but they can't do certain things. But for purposes of the file system manipulation, they'll be a super user. Or for purposes of some other utility, they'll be the super user. It's just a different group of users who are allowed to do more than the admin can do, or the secretary can do. Because you certainly don't want to make someone with very little Unix background knowledge, you don't want to give them super user privileges because they'll be reformatting hard drives and stuff for you. So, kind of makes it so they can't make problems. So, and well, this is funny because even if you are a super user, you can go sudo, sudo space something, and you can get it something. You can become the admin. Because if you have the admin password, you run a sudo, you're sudo admin. So you can pretend like you're the admin if you have the admin's password instead of logging in as the admin. The reason why you do that is because then the system can track you as a user. It was bhacker that made the change, not root. Oh, but although I got in through sudo. And so I can still own files that I'm using as I'm logged in as the admin temporarily. And I can still have access to admin directories and things. But everything I do still belongs to me, it doesn't belong to the root. Versus giving your name and password out to someone. Hey, just log in as admin. Different. They're logging in as admin. So there's an elaborate set of utilities to allow people to log in as admin without logging in as admin, essentially, to give them different levels of privileges. So upon creation, default permissions give to a file modified by process umask value. So there's a umask value that's associated with who can modify particular files, usually the user, the owner of the file, or someone who has privileges to it. So the three types of permissions that we've looked at already, so this is, I'm going to kind of skip through this because we've seen this already, but then the three sets of permissions that are associated with it. So the three types, read, write, execute, and you can read through this a little slower on your own. The three sets are for the owner, the group, and other. Other would be maybe the world, maybe any group that might be defined. Also, checks are made against the process's effective IDs as well. Relatives and effective IDs are absolute and effective. And going back, this is down memory lane because we've done this before already as well. The change mod command and the symbolic access. So example would be change mod plus R plus RWE or something. So you can use the RWE, and as one student in this, I think it was this class who pointed out, not every operating system is actually going to support the letters versus the numbers, and it's always safer to use the numbers actually. And mostly Linux tools that are used for web development, FTP tools support the numbers actually. They don't even support the characters. So if you're having problems getting the ERWs, if plus R is not working for you, then calculate out the number. And you can use this actually as a good reference. Just print this out, you can use it as a good reference. In fact, this is what a lot of people do actually. They get a chart like this and they go, 0, it's no, no, no. Okay, 1. And then you only have the three groups, so you go, as an example, 777 gives the three levels. Owner, group, and other gives them all yes, yes, yes on read, write, and execute. Kind of dangerous. Or you can go 0, 0, 0, and there's a number for each one of the different user, owner, user, group, or other category. There's only 3 different categories. Directory permissions work the same way. Same type and set of permissions as files. but nobody ever thinks about putting it on the directory. They only put it on the files. But if you can get into the directory, if you have read access on the directory, aren't you reading what's in the files? So read means a process may read a directory, list the files, but they can't read the files that are in there. They can just list the files. Write means a process, they add or remove files from the directory inside of the directory. So you can have write access on a directory and delete a file, but you can't read it, perhaps, maybe. It depends on the file attributes. Or execute process can search access files in the directory or subdirectories. So it's a hierarchical set. And here's some command utilities for managing files and directories, and this is again going down memory lane, but it's kind of putting it all together for you. We've looked at we didn't look at the links. We didn't look at print a file LP either. And this depends on what LPT1, LPT2 are assigned to in terms of what printer that's going to go to. Word count. I mean, this is interesting. I still have this around. In the old days, people were interested in the counts of the words inside of a file, just for the size of the file, I guess. I don't know. Word count is still around, still being used. Because you can actually see if a file is changed, if the word count's changed. But you can switch a word without changing the count, so I don't know. I don't know, but anyway, this is just for your reference, a list of common commands that might be done. There's really not that many commands, actually. So going back to the Unix process concept, because outside of files, directories, rights, users, processes, what else do you use the computer for, really? Run programs, users, that's about it. Print. Print's kind of trivial, actually. Some definitions of the program, we've seen this before, so I can kind of go through it. Collection of bytes, data, image. This is different. The image is the computer execution environment. The image, the data. This is what the proc directory is actually giving you in the file system. The proc is actually a separate type of file system that is accessible, that's mounted. So you'll see it in your mount file. You'll see proc at a particular location. It's a separate file system in itself because it's formatted to match the memory, essentially. Process is the image itself. Execution of an image. Multitasking is many processes executing simultaneously. And we've seen the foreground process group. We've seen the process ID and the group ID. What we haven't seen yet is this foreground process group and background process group. So both groups are actually separated out, as you might expect, from foreground to background. And so we can query the group, list the group out, and then we know how many are in the background, how many are in the foreground. Kill all the background, kill all the foregrounds. So we can treat them as two separate groups if we want to, in terms of the access. So the processes group associated with the terminal at a time. So processes in the background are not in the foreground group. So it's two separate distinct relationships. So the process spawns another one using the fork system call. And might be able to put a number in here in terms of, this is strictly going, usually the fork system call doesn't take on a parameter. It depends on the library that you're using. It's going to be essentially either a parameter that for which you're going to keep track of this piece of information, keep track of that, or it might be implemented in a slightly different fashion. Normally, and I should take this out of the slide, you're not going to see a number in the parameter, you're just going to see fork. Just execute fork. Fork returns a process ID of a new process that was created, and generally you're not going to run it with, the parameters. Let's see, creating processes in the parent process, which is what you're doing when you run a fork. So the newly created process is the child process. Fork returns 0 to the child process to say that it was successful, and it returns the process ID of the child to the parent process. So the parent always knows about its children, and the children don't necessarily know who the parent is. But when they signal on a exit, on a termination, the parent actually automatically gets signaled. So sometimes that actually gets lost. So and then they become a daemon. So exec, actually exec is going to take, and this is the number of parameters that might actually be listed, which is kind of confusing, I believe. That's why I'm going to take it out. But exec is like a lightweight process. So you fork a process, then you run exec. Exec goes out, runs a program, ends, automatically comes back, cleans up easier. Only allocates memory for the program, doesn't really get a copy of the parent's memory space, it doesn't need it. So to run a new program, a child will execute an exec system call, overwrites itself with the code that it runs, initial data from the new program that gets loaded in, thus initiating execution of a new program. And then when the program ends, it automatically gets cleaned up. It's a lot easier. That's why it's called a lightweight process, because exec is just made to run a program. It's not going to fork off another process. It's just going to essentially execute something. So shell programs are usually a main process with a bunch of execs that are run from the shell. And the shell environment is running those execs, which are processes. So everything you run on the Linux prompt, whether you realize it or not, is a process. Everything runs in a process. So waits, the parent can suspend its execution until one or more of the child processes completes, and it performs a wait system call. And believe it or not, only one process at a time can complete, can actually run. So it has to share the execution, and so the child's either waiting for the parent's waiting for the child, somebody's waiting for somebody. Because they're sharing the same memory space, if you think about it. One person at a time is going to be doing some work. Everybody else is waiting. So exec, exit, and again, whether they go exit 0, exit 1, 0, exit 2, exit 3, depends on the parameter list given for the function implementation. Upon termination, the process can set an exit status available to the parent. So the code uses a 0 for success and non-0 for failure of some sort. So it can send out, exit 2 means I died and I didn't clean up my memory. Exit 0 could be I died successfully and I cleaned up my memory. You don't have to do any work. So that's good. Here's an example. It's a program that creates a new process to copy files. This is the main program. It assumes it has two arguments, a source and a target file, that are being taken in from a command line prompt. So we have the check to see if the fork is equal to 0. If so, we have a child process. If not, we don't. And then if so, then we run a cp command. And execl is one of the switches. And we have exec vp, pl. I think there's a G in there too. And they're all different forms of the same. They're different method. They're different functions all doing the same thing with different numbers of parameters and doing different purposes. They serve different purposes, essentially. So you have to imagine this is for object orientation. We don't have any polymorphism. And we don't have any, we have a different function for everything. We don't have any objects here either. It would be nice to see, actually, an implementation, an object-oriented process implementation. So one of you who goes on to be a doctorate student, you can do an object-oriented process implementation for an operating system. And there's a couple of people working on that actually right now. Object-oriented file. They have object-oriented file systems. There's a couple of object-oriented operating system ideas out there, which are kind of interesting. Everything is an object anyway, right? In the real world. And in the programming environment, everything's an object. So here's a fork operation. After the fork operation, we have shared text, and we have a parent process data, and we have child process data that comes out of the shared text area for the process. Because of the family tree, everybody's related, everybody has access to the memory. After the exec of program number 2 in child, so program number 2 is the cp command in the previous example. After the exe for program 2 in the child, we have the parent process data, we have the child process data, we have the program text data that's unchanged over here, and over here we have program number 2 text data in the child. So each person who's changing something in terms of, let's say in this particular example, the exec, they only have access to their own process space, so they can't destroy anything else for other processes. So using multiple processes actually allows you to kind of like the same purpose like a file system does. It allows you to create directories and files and structure too. It also is processing. So it gives you, especially Unix people, love the ability to be able to organize their memory, organize their running programs and stuff, just like you do file systems. People in Windows, they just double click on stuff. Essentially, you're running processes every time you double click on something. And the stuff you have minimized is running in the background. You want to think of it that way. And the window you're working on right now is running in the... Can you really run two at the same time simultaneously? Yeah, actually you can. You can have something running and then minimize it. It's still running. Like right now, I think I have an upload. Hopefully that upload is going to finish before my lecture does. So maybe, or it may have died actually already. I don't know. Sometimes if the internet access doesn't work, the upload's going to fail, and I wouldn't know it because I got this PowerPoint covering my entire web browser so I can't see it. So. But that's multiprocessing. Think about it. I got two separate processes. I got a PowerPoint process going on. I got a upload process going on. It's multiprocessing. Where would computing be without it? Started with Unix. And here's the Unix process genealogy, the family tree. We have a process generation in the beginning. Init process number 1 forks, and it forks the init process. And then we have init that runs in exec, the init that runs in exec. Oops, there it is. 3 execs as an examples. For 2 of them running a Getty, it's going to be a shell interface. Maybe Getty's going to run a login. Or Getty's going to give you the ability to run a shell interface. Let me just say that. And that's simplified. A login, and the login's going to have a shell. And so we have hundreds of users at any one time, all running from init essentially, in their own little threads. And then this shell guy, he might be running VI or something, and this might actually go out to another shell and another shell. And the sky is unlimited, essentially, on the number of processes that can be created. But keep in mind, all these processes are taking up memory. So sky really isn't unlimited. It's memory related in terms of how big that family tree is going to get. So. All right, so process permissions, we've actually gone through this stuff already, but the effective user ID and the effective group ID determines the process access to the read-write search files. So going to reiterate a point I haven't made already, I've pretty much talked about, I think I've talked about the real IDs and real group IDs and stuff, but if we want to talk about the relationship between the groups and the file access, this is why you probably want to make the process a member of an effective group or something, an effective user ID. So processes can be owned by groups of users instead of user individuals, and if that's the case, then the process has access that are set for the particular permissions that are set for that particular group. That's what this is basically saying. And umask is going to be the file mode creation mask. Used when a file or directory created by a process. So we can run that command to kind of see the information that's associated with the process. Signals, your formal definition of a signal. I talked about them already in terms of passing them, but really haven't defined them in terms of a system administrative kind of tool. It's a message a process can send to another process or process group to signal a group. And if it has appropriate permissions, then the processes will receive them. The message number represents the symbolic name of the symbol of the signal, like a kill, a start, a pause, a resume. And when you perform a shutdown command as an example, the kernel actually sends the signal out to all logged in users with a notification. That's it. And it catches you by the process, because each user who goes into an init who creates a shell has got a process that's identifying that user. So if we can use the process system to identify the users, we can send them spam mail. We can send them system announcements, notifications. It's also used in the opposite direction for a system user to say, hey, where are my resources? Why am I, shut me down, clear everything out. So when you exit a shell, you're sending a signal to the kernel to say, hey, I'm gone now, I'm going away. So for each signal, there's a receiving process the kernel actually has to do. And it queues up the signals because it has its own signal handling process. Explicitly ignore the signal, maybe specify some action to be taken upon the signal receipt by the signal handler, or otherwise some default action that takes place. Usually a process is killed or something happens automatically when the signal is generated. And here's an example, kind of put it into perspective. When a child exists, it sends a sigchild signal to the parent, and that's how the parent knows about the child ID. Knows how to get a hold of it. When the parent issues a wait, it tells the system it wants to catch the sigchild signal, which is why a parent always waits for the child. So if the parent's running, the child can't run. So the parent waits, the child signals, so that we have that communication going on, and then the child can run and do whatever it needs to do. When it's done running, the control goes back to the parent, and then the parent can start running again. So when the parent does not issue a wait, it ignores the sigchild signal, doesn't even know the child exists. We can actually create a zombie that way by ignoring it. And that actually can eat up it can actually eat up resources. Zombie processes are not good. It's like the parent created it, but never waited, never let it run. It's like accessing resources, allocating resources, allocating over and over again, but not using it. So In terms of interprocess communication, that's where we get this signal, where we have the read and the write on regular files, as an example, in terms of related processes. We also have this concept of pipes that we use, which is really interprocess communication. If you think about it, one of your assignments is going to have you use pipes heavily. I don't know if you've gotten there yet, but you have to run a command and then send the output of the command to another command via pipe, which is that up and down line, so you can string commands together. Well, what are those commands? Is one process sending information to another process, sending information to another process. So you're kind of lining it together. So when process B tries to read from the pipe, returns data if process A has written to the pipe, and returns end of file if no other process has pipe open for writing. So you can read and write through the pipe interface. It suspends execution until the process A writes the data to it. So it's actually, pipes are really a form of automated interprocess communication, sort of like signals in a lot of ways. The second one's not going to work until the first one completes. So if there's nothing written, there's not going to be anything read yet. So it solves all the processes, all of the headaches of interprocess communication and some of those traditional IPC problems. And the child returns an exit value to waiting parent process when they're done, in terms of related processes for interprocess communication. And an unrelated process might be named pipes. That you don't really have to worry about for this class, and it's not supported on every system either. But you can kind of pre-configure the pipe and use it in unison with multiple commands. Message queues, not always supported either. Semaphore is more supported than anything else these days. Shared memory, always supported. In fact, usually the user mode will use the shared memory model because it's the most easiest kind of interprocess model to use. Sockets, used a lot now, obviously. TCP/IP and a lot of the UDP and a lot of the other protocols are using sockets as a lower level implementation, which is a traditional standard Unix technique. So process environments include, we've seen this already, it's kind of a, well, actually there's some new stuff on here. We got the process ID, we got the process group ID, but we also have the open files that are owned by each process. So the environment space that's used, the memory that's being accessed, has a link to all of the open processes, all of the open files that are owned by this process. Also the current working directory, really effective user and group IDs, file creation mask, which is the UMask, resources, all the limited limits, signal action settings, and a set of named local variables and things that are in the environment. The entire environment space is actually kept by the process in terms of the process space. And then we have this concept of the file descriptors. Again, going back to the pointer concept. And really, what is this pointer to a file? It's a file descriptor. So each process associates a number or a handler called a file descriptor with each one of the open files that it has. So you're doing a C program, you can actually create a file descriptor yourself. And it's an integer value that's returned from the open command. So you're running a system call, open, to open a file. And it returns to the kernel, which sends up to the user the file descriptor, which is an integer value. And in your C program, you can do exactly what the kernel is doing, because your process is keeping track of its files, and you have access to your files. You don't have access to other files that are opened, but if your process created it, create a file descriptor. You just an integer value, and you take that integer variable and you make it equal to the file, and then you access the file through the descriptor, essentially. You say, and if you've ever done C file fopen commands or just using the low level open, that's what's going on behind the scenes. It's just using the kernel data that's associated with the process. Kernel's got it. Why not just give it to the user, which is a system call. Open is a system call interface. So login 3 files are associated with the terminal. The standard IO, standard output, standard error. And everyone thinks, oh, this is really fancy. I'm writing to stdio, standard IO. What does that tell you? Well, you're writing to input output. What you don't realize is you're actually writing to error automatically too. But nobody ever checks the error. And then you can do file redirection, where you can send the contents of your IO, your standard IO, to somebody else's terminal window, or to a file, or to output, input to output, or send it all to error, or get rid of it all. Send it all to a file so that your foreground looks like a background process running. So file FD0, file descriptor 0 is open for reading. FD1 is for output. FD2 is for reading and writing, so, which is the error. So process inherits the parent's file descriptors unless it's specified. Close on execute, exec, when you run a program from the parent. So the children have access to all of the open files that are owned by the parent in this particular scenario, because it gets access to the memory space. Why not the open files too? Here's some process subsystem utilities. We've seen PS, we've seen kill, terminates the process. We've seen wait for the parent to wait for one of its children to terminate. We've seen, no, we haven't seen no hope, which is makes a command immune to the hang up or terminate signal, which means it's not going to do that. Not going to follow the rules. Sleep or nice run a process at a lower priority. So set user ID or set group ID mechanism. So we saw the change mod to change the file permissions. We can also use these as set user ID and set group ID to change the permissions, or the who's the user and who is the group associated with the particular process or file. The mechanism effective for user IDs are different from the real IDs. When it executes a set or a set group or a set ID, process is effective becomes that of the executable. Example, changing your password. So it might not necessarily kind of changing group and user IDs is kind of dangerous in some ways, because when you set, everybody gets the same information. Security problems, permissions on executable files, perhaps, and directories in which it contains contain must be correct, otherwise especially replaced by Trojan horses and stuff. In fact, this was the primitive viruses that were out, actually. People used to have everything opened up, and if you didn't set permissions correctly, every Unix system's the same. There's a bin directory, just go ahead and delete the bin directory, okay, or just replace this file with another file, because you can, because they left it open. So then people got smart, and they started locking stuff down. And then some systems remove the set user ID and the set group ID bits whenever files are modified as a security precaution. So you can't, make admin a member of the group ID HR. And then all of a sudden, HR is going to, just all now they have shared permissions or something, or I don't know, or HR member of the admin group or something. And then HR people can do admin-related stuff now, which is not such a good thing. A slight overview of the shell environment. Command line interpreter, we know what those shells are at this point. And it's a language between the operating system and the user. It is our shell. Our user is selected by a shell by running, and we've seen how to run a shell already. We haven't seen the directory path bin, but most of the shells are stored in bin. Gives us our C shell or K shell. And then we have the concept of shell scripts. Nowadays, almost every shell is the same. All shells are going to support the same thing. Shell is almost as generic as it can possibly be at this point. In the beginning, we had a shell that was designed for this purpose, a shell that was designed for that purpose, and they all had special user purposes. It's kind of like we had different types. No, we just have a DOS prompt. We had different types of desktops in Unix. Now there's pretty much all the same. And Genome or KDE is pretty similar in functionality. They all have icons now, GUIs. And so it's a little bit different, because in Windows we think of the shell as the operating system, which Windows is really the shell. The GUI is the shell you're talking about. What version of Windows you're, well, actually it's one and the same, I shouldn't say. So in terms of working with a shell, from a Unix perspective, it's invoked automatically during a login. So usually your login script is going to start your shell automatically for you. It could also be done manually and prompted by the user. And it reads a specific file for initialization, usually a shell script for startup. And it displays the prompt, waits for user commands. That's essentially all it does. Execute user commands, go to step 2, unless you press Control-D, and then the shell terminates, or type in exit or end, depending upon your shell. And inside of the shell, what you've got is your temporary user space in the user mode, for which you're running commands that you're interfacing with the operating system, kernel, you're interfacing with the file system, you're doing a bunch of manipulation. So this is where I said you can redirect output. and input and pipes and things. And these are the symbols you actually use for it. The double arrows, and this is for those people who love C++. IOStream is using this C in and C out. This is where these symbols are coming from. They're strict Unix commands for IO redirection is what this is. C in takes in through arrows going this way. Input goes this way. Output goes this way. So either single or double arrows to indicate. The C++ library uses the double arrows. Most of your Linux prompts are going to use the single. Why do they implement the single? I don't know. If I were writing that API, I'd use double. I mean, I'd use single instead of double, but I don't know. Interesting. So man ls, well, take the output of ls and send it to this file. That's what this is doing. This is like doing cout, essentially. Or input, concatenate, bring it in from input.data. Or pipe, cat file, send it to wc-l. So it counts the number of lines in this particular file. So take this file, and cat's sort of like a text, like a print it to the screen. But cat can be used for concatenation, which is what, so you can cat two files together. Which is, what are you doing, printing them together? So some of the terminology is kind of weird. Dates back from, primitive computing. Some core shell features, and this is supported usually by most of the shells these days. Simple complex commands that are shell specific. Redirection IO, that would be whether you're using the single or the double would be the question. The C shell actually uses the double, which is probably why C++ uses the double, I would say. But your average bash shell and your corn shell are using single redirection. So it's kind of a little difference there, but it's really accomplishing the same task. The syntax is a bit different. So it's doing the IO input, output, redirection. Pipes are supported in most shell environments. Wildcards, command substitution, using using variables actually in there. Background processes, shell variables. Here documents, built-in commands, programming constructs. Depends. If you've got a shell that supports C, a shell that supports a Perl interpreter, Python interpreter, PHP interpreter, those are all running in shells. Those are all shells. Not native Unix shells. They're open source utilities, most of them. But they're still part of Unix, and they came from Unix in terms of functionality or languages. Command support, simple commands supported, simple commands, sequences of non-blanks, arguments. The concept is the same, the first argument, the second argument, the command switches, the parameters, along with commands. Some shells have a different format. They don't use spaces. They might use opening and closing brackets like functions. If you were looking at a Prolog shell, you're going to be running functions and stuff, which is kind of slightly different format. Enter remaining arguments with a few exceptions. See meta characters and things. So you pass arguments to that command. So command parameter passing, file names, directories are all pretty much used consistently among all shells. In terms of the complex commands, we've got multiple commands that can enter in, command groupings, conditional command execution. If this happens, then do that. That happens, then do this. Wildcards, and if you think about programming languages, this is where all the stuff's coming from. Can you run a function? Can you run a function with one argument, two arguments? Can you string commands together? Can you run outside commands, inside commands? Are you going to have if, then, else, flow control, stuff like that? All that stuff. Shells is a combination between the user mode, running of commands, and programming. If you think about it, Unix was designed for C programmers to begin with, so the shell is going to be highly supportive of C programming syntax. So, wildcards, using the asterisk, using the question mark, list. List matches any character in a list. Upper, lower matches any character in a range. Upper and lower inclusive. So one of your assignments actually has you run a bunch of stuff. Find command, a bunch of other things in the shell. And you'll see there's, depending upon your shell environment and your Unix system, your BSD versus your Solaris versus your Linux breeds, you might have different commands, and the command structure might be slightly different. There's going to be a lot of similarities though. Shell scripts. That's another common thing among most shells. They support scripting. What's scripting? Well, storing a bunch of commands in a file, and then running the file. It's essentially a script. So a Perl, it's going to be a Perl file, a .pl file that you're going to run. The shell interpreter is going to take up that file and execute the commands for you. So shell script is a regular old text file that contains the shell or Unix commands. And before running it, you actually have to make it executable. So you give it the executable change mod plus X. Ooh, with the file name, that is really weird. That woke me up. Very useful for automating repetitive tasks, backups, stuff like that, administrative tools, storing commands and stuff. So when a script is run, the kernel determines which shell it is written for and examines the first line of the script, which is why most of the shells start out with this number sign in the beginning. So the first line generally contains a hash symbol along with, is it a C, is it Perl, is it Python, what is it? And so it knows what to interpret it with. And then if the first line is the form of a path name, then there's an executable file that the shell actually runs. So, and the path name is used to interpret the script, essentially. So this is where we get Perl. You'll see this at the beginning. And if you're running the Perl CGI assignment, you'll see you have to actually put in Perl interpreter. This is the version number we want you to use. And you're writing a script in a text file that's being run, and it's looking for the interpreter, and it's going to run it. And I'm actually going to have a lecture on Perl and CGI later on in the course as well. So just if you're wondering. Some of the assignments we haven't quite hit, so the projects we haven't quite hit yet. But we're getting there. It doesn't help when we keep having days off, which is why I'm taking us to the full length today, because we have to catch up. So if either rule is a 1 or 2 applies in terms of the above here, the script is interpreted in a Bourne shell. So it actually, when you run the script, it actually opens a shell for you. So you don't actually have to be in a shell to run the script. So you can, well, you're in a shell anyway. It can be a terminal prompt, which is a shell. You load in the name of the file, which is an executable file. It will open up a shell for you, and it runs in its own shell environment. It doesn't actually share the same shell space. It runs just like a program does, actually. Creates a new process. And then we have this concept of here documents. As I mentioned before in a previous list of items that were listed as features of shells. Shell provides alternative ways of supplying standard input to commands. So it allows an inline input redirection using the redirectional operators called here documents. And that's essentially just the terminology, arbitrary delimited list of stuff that's coming in as an argument. So it's just nothing more than a shortcut or an alternative way of providing the input. Instead of coming from the terminal, the keyboard, it can come from a here document, which is, give me the list. Here it is. Here's the document. Here it is. And give it to the command. So it's like, give me a list of files that are on the file system. Okay, here it is. So it's kind of similar to piping. Kind of, you're taking from one document, you're sending it in as input to a program, and you're running it. So what is this? Arbitrary delimiter should be a string that does not appear in the text. Shell variables. Talked a little bit about this already. We're going to see this in a shell lecture coming up, where we have several different mechanisms. The variable actually has a name. We have the environment variables, but we also have temporary variables that we can create, just like in programming, and use them inside of the shells. Some of them have types, some of them don't. Representing a string variable as an example. Shells can save time by reducing typing errors for variables. So some variables, like the C shell, you can actually have types. Other ones you can't, or you don't have to. You can just say A is equal to this. Okay, Or you can say that A is a string, or A is a number. And we'll see that. I have an entire lecture on shells scripting and using the C shell. So it allows you to store and manipulate information, same concept as in a programming language. So local are set to the user on the behalf of the shell. Only the scope is within the shell itself. It doesn't extend past the shell. And positional parameter variables are normally set only on the command line, essentially. And here's some environment variables. Keep not to confuse with variables that you can create. We can also just have variables. But environment variables go past the shell life. So you can set home and a login script. And every time you go into any shell, you have access to home. So it's multi-shell visibility. So it's global versus local variables, which is going to be local scope for the particular shell. When the shell goes away, so do all your variables, if they're local. They're not a global environment variable. So home, we've seen path, mail. Actually, believe it or not, Unix has its own mail system, email, built into the operating system. It's not like an afterthought. Nobody ever uses it. Well, okay, let me rephrase that. No, nobody ever uses the command line mail tools anymore, like Pine or some of the other mail tools. No, you're going to configure a mail tool to get your mail from your mailbox. That's what you're going to. It's going to be a GUI tool or something. So, absolute path for your mailbox. Your mailbox is the same as on a Windows system, actually. The user ID, absolute path for login shell, where your shell, what shell you have, what shell are you using, the type of terminal that you're using. So we have positional parameters that might be set. So when a shell procedure is invoked, the shell explicitly creates positional parameters. So the name of the position of the parameter is a number, like first, second, third, fourth, sixth. Very similar to command line arguments. When you run a C program and you have argument 0, 1, 2, 3, comes into the form of a variable. This is where it comes from. So this is positional parameters that are used mainly in scripts. So number 0 is the 0 position on the command line. 1 is the first argument. Actually in C, I think 0 is the name of the program you ran, which is 0, the starting point. And then 1 is the first argument. So if you typed in my program space me space you, you're sending me and you as two parameters positionally as 1 and 2, and 0 is the name of the program that you ran. If you've ever tried to parse command line inputs in C, that's what you're working with. Same concept comes out of the shell environment. So you can have any number of parameters. It's dynamically allocated by position number, separated by a delimiter, normally a space. So, usually space, actually. So quoting restores the literal meaning of the characters that are being processed, especially by the shell. So same concept. Literal quotes are not passed on to the command. So single quotes exhibit wildcard replacements or command substitution. Double quotes are basically replacement only. So, and the quotes are nested. Only the outer quotes will be effective. Built-in commands, we all know about those. ls. It's a built-in. No, it's not really. It's part of bin. What are kind of built-in? We don't have built-in commands in shells. Yeah, you can have jobs. Most of our built-in commands are like system commands these days. But you can create some commands of your own in your own shell if you want to create your shell. So the commands that are internal to the shell. Well, actually, the Perl has its own commands, and if you go into a shell interpreter for one of the scripting languages, popular server-side, faster to execute, more effective than other commands normally because they're built right there in the program. They're command like switches and stuff. Oh, the arrows. And the history. There's a history of the shell is built-in commands. And the shell does not have to fork off or execute a command. It's there for you right now. So it's part of the program that you're running. Trade-off or redirection, input, output, not allowed for those types of commands because it's in the process. If you think about the concept, here's some built-in commands. You're not running an AXCC. You're not forking off anything. So you don't have any information to share. You're running it from within the same process. So here's some built-in commands. To the common 3 shells, echo to put something on the screen. It's kind of doing a print it to the screen. CD, change directory, wait, exit, eval, mask, shift. So it seems like a lot of subshells. No, let's not do subshells. You want subshells? Or you want next time? Oh, I never covered the subshell. It's just one last little slide on there. Shells within shells. So if you're actually here, I'll put it up now that I mentioned it. Subshells. So when a parent forks off another shell, it's a shell within the shell. So you have different groups of commands that can be executed in each one of the shells. And so you can actually have one shell fork off subshells, like 5 different subshells, and then you can talk between the shells if you wanted to. Or you can keep them all separate. Because you don't have to have just one shell. In fact, some users just do that. They're in a shell, and then they type in a shell command to open up another shell, which is inside of that shell. Why? I don't know. Well, I'm sure it serves a purpose for something. Especially if you're using a special purpose shell. Well, we all do it in terms of how Python, Perl, and PHP, and all those scripting languages are run in Unix. If you're at a terminal prompt, you're going to type in Perl. Usually you're going to type in Perl space the name of a Perl script. But you could just type in Perl and use the commands through the interpreter. Well, that's a shell, Perl shell, inside of your shell that you're in. You can't go from Perl to Python or PHP, that doesn't work. Or if you're on a MacBook, you go to terminal, you're in a shell. You type in Python, you're in a shell. You're in a Python interpreter, and those are all shells. Windows is a shell, the Mac OS X is a shell. It's running on top of BSD. If you think about the concept, well, users just using shells. But if they called it a shell, people wouldn't like it, so they call it Windows. Or OS X. Or, you know, something a little bit more friendly. So, questions? We don't have a midterm for this class, so I don't have to talk about a midterm today. Is that right? We don't have a midterm? I don't think we do. We have tons of projects and assignments. Yeah, we have too much projects and assignments, but we don't have any midterms. So. And other classes, I was talking about midterms this week, but not for you guys. Our class isn't over until August, actually. So we are at the midterm. So, all right, if we don't have any questions, we're done for today. We're done? No questions? Okay, good. We're done. Thank you.